Okay, this is chapter 14, soil resources. An overview of your chapter. We're going to be talking about the soil system, soil properties and major soil types, environmental problems related to soil conservation and regeneration. Right now, I'm gonna let you guys know that I will be mentioning the things you will need to know for the exam. So pay attention. Soil is incredibly important, and it is the relatively thin surface layer of Earth's crust consisting of minerals and organisms, as well as organic material that has been modified by water, wind, weather, and those organisms. It's easy to take it for granted, right? We don't really think about how soil virtually supports all terrestrial food webs, and it is an evolving system that, with several organisms and physical properties that interact. So, what forms soil? Well, the weathering of parent material, the time, um, climate, organisms, and the topography. Soil composition, the four distinct parts of a typical soil. Well, here you see them, mineral particles, um, organic material, water, and air. It occurs in layers in which each layer has a certain composition and special properties. The plants, animals, fungi, and microorganisms that inhabit soil and interact within it use soil to go through their life cycle, and that's incredibly important because when they die, they decompose and return those nutrients back into the soil. Soil pore space. It occupies 50% of the soil, and it's basically air and water depending on how saturated the soil is. It contains a certain percentage of air, which allows for oxygen and hydrogen and all these different gases to flow, and that is aeration. And water is also important because it is used by roots and microorganisms. Water, however, can leach out of the soil if it's not exactly rich soil that can withhold water, and then it carries dissolved materials, minerals, elements further down. Alluviation is an important vocabulary word, and it's basically the deposition of leached material into the lower levels of soil. Soil horizons. If you were to make a deep vertical cut through a soil piece, you will see that there are distinctive horizontal layers, and we call that soil horizons. A soil profile is a vertical section from surface to parent material showing the soil horizons. So what you see on the right side is a soil profile. And the uppermost layer is the O horizon. It's rich in organic matter. It is primarily filled with plants, litter that gradually decays. Right underneath is the A horizon. It is also dark and rich with accumulated organic matter and humus. Plant roots and soil organisms are plentiful in this horizon. And then we have E horizon, which has the heavily leached material from A and B horizons. That develops between A and B horizon, right? So it's kind of like a transition layer between A horizon and B horizon. B horizon is a light colored subsoil beneath the A horizon, and it's often accumulation of nutrient minerals that have leached out of the topsoil. And finally, beneath the B horizon, we have the weathered pieces of rocks in the sea horizon. Sea horizon is also below the extent of roots, and it's often saturated with water. Soil organisms. Although they're usually hidden underground, their numbers are massive. This is where we see insects, bacteria, fungi, algae, nematodes, protozoa, and that it could be millions of them just inhabiting 1 teaspoon of fertile agricultural soil. Most numerous in soil are bacteria, and they number in the hundreds of millions. Scientists have identified around 170,000 species of soil organisms, but thousands remain unknown. These soil organisms provide very essential ecosystem services. They maintain soil fertility by decaying and cycling organic materials. They prevent soil erosion. They break down toxic pollutants, they cleanse water, and they even affect the composition of the atmosphere because these microorganisms can be nitrogen fixers, which if you remember from one of the earlier chapters, nitrogen is an essential element that it occurs as a gas in the atmosphere and needs to be fixed by microorganisms on roots to then be used by plants. Here you can see those ecosystem services that microorganisms provide. Another very important one is castings. Castings are bits of soils that have passed through the gut of an earthworm and then are deposited near the soil surface. So in this way, it's basically nutrient mineral cycling, bringing those nutrients from a lower level up to the up to higher levels of soil. Mycorrhizae is also very important. These are symbiotic relationship fungi between the roots of vascular plants and that can help absorb nutrients better. The most commonly known mycorrhizae relationship is that between orchid roots and the mycorrhizae. So it's really interesting that they can basically have a mutually beneficial relationship. Nutrient cycling in soil. So casting is just one type, but really there's a pathway of several nutrient minerals or elements from the environment through organisms and back into the environment. And you can see it here. Essential nutrient minerals such as nitrogen and phosphorus are cycled from the organisms, from the soil to the organisms, and then back to the soil. So that is really important, and I just want you guys to remember this. However, it is going to be on your exam. Soil texture. Texture and acidity are the two parameters that characterize soil. Soil texture refers to the relative proportions of different size inorganic minerals such as sand, silt, and clay. Soil texture does not refer to the organic material in the soil, only the inorganic minerals. And the size assignments are sand, silt, and clay, which give scientists a way to classify soil texture. Particles greater than 2 millimeters are 2 millimeters are called gravel or stones, and they're not really considered soil particles because they don't have any direct value to plants. Right after that, between 2 millimeters and 0.05 millimeters is sand. Silt is 0.05 millimeters and 0.002 millimeters, and then clay is the smallest one, being less than 0.002 millimeters. How does soil texture actually affect the properties of soil? Well, basically, it influences how plants will grow, how it will retain water. So a very simple science experiment that you probably did as a child was running water through sand. It has pretty good drainage. right? Because it's a little bit bigger than clay, which is small and has a higher surface area. It decreases leaching, so water can't really flow through it as fast as sandy soils. Um, so when you want to have a healthy soil, you want to have a good mix of these for your plants. Soil texture also influences how soil minerals retain ions, positively or negatively charged ions such as potassium or uh, OH minus, right? And these ions are essential for plant growth. So if the texture is not able to hold on to them, then it just leaches out. A loam, which is an ideal agricultural soil, has an optimum combination of different soil particle sizes. It it contains approximately 40% of each sand and silt and about 20% of clay. Generally, the larger particles provide structural support and aeration and permeability to the soil, whereas smaller particles bind into aggregates or clumps and hold the nutrient, minerals, and water. Soil acidity, we measure acidity, of course, with the pH, which stands for potential hydrogen, and that's the amount of hydrogen ions within a solution. The pH of most soils ranges from 4 to 8, and as you may or may not know, 7 is neutral, 0 to 6 is primarily acidic, with 0 being highly acidic, and then 8 through 14 is basic, with 14 being the most basic. So pH seems to be mid-range. Most soil stays, mid-range 4 to 8. pH is incredibly important because it affects the leaching of nutrient materials, since the solubility or the dissolution within a mixture can occur. Optimum soil pH is neutral, 6 or 7, because nutrients are most available to plants at this pH. It's also the most optimal and what is usually found in water. The pH of water is between 6 and 7. Acid precipitation from air pollution, primarily from industrial emissions, increases the acidity of the soil and can cause forest decline. However, we have found that adding calcium can restore pH balance, because that is an element that makes things more basic, right? So it's increasing the pH. The major soil groups: variations in climate, local vegetation, parent material, underlying geology, topography, and soil age result in thousands of soil types. Soil taxonomy is the way that we currently classify soil into 12 distinct orders, and then it's subdivided into over 20,000 different soil series that vary by locality in the US. You do not have to know all these. We're just going to talk briefly about the 5 most common soil orders, which are sputosols, alphisols, mollisols, aridosols, and oxisols. If you look on page 287, they talk briefly and show you what each one of these looks like and what it contains. You do not have to know them. I think it would be a little bit too much to make you all know the exact soil groups, even just the 5 ones. I don't think it's that important for someone to know, but if you're very much interested, look at that on page 287. Environmental problems related to soil. This is really what we should be discussing. As we have seen, humans disrupt all systems. This is also true for soil. We talked about the management goal for water. Well, there is a goal for soil as well, and it includes sustainable soil use, which is the wise use of soil resources without a reduction in fertility, so that the soil remains productive for future generations. And soil erosion is probably the most common problem, and what occurs is wearing away or removal of soil. It primarily occurs through water and wind, and it causes a loss of soil fertility as organic material and nutrients are eroded. More fertilizers then have to be used to replace nutrients lost through erosion, which alters the nitrogen cycle because, as I mentioned previously, the Haas too much nitrogen and too much nitrogen production can also be bad. Soil degradation came to a head in the 1920s with the Dust Bowl and severe soil movement, just erosion and loss. And because of that, the National Resources Conservation Science, formerly called the Soil Conservation Service, is a national agency under the U.S. Department of the U.S. Department of Agriculture that measures the rate of soil erosion at thousands of sites across the U.S. The good news is that soil erosion, because of proper implementation, proper conservation and management practices, has increased between 1987 and 2007 by about 55%. Okay, has declined. Soil erosion has declined. As you can see here, variation in soil degradation is widely different between continents, with Europe having a very high rate of soil degradation. And soil erosion, which I already mentioned, increases movement of sediment among systems into streams, waterways. It increases water pollution because what we're seeing is more sediment being deposited, and those sediments may be binded or contain minerals or elements that could be particularly toxic, such as mercury. And degradation of water infrastructure because it's just constantly beating down these structures. Erosion accelerated by poor soil practices. I already talked a little bit about this, but this is just an overview. The American Dust Bowl, which I also mentioned, occurred in, sorry, not the 1920s, but it occurred in the 1930s. The Great Plains has low precipitation and is subject to drought. Natural vegetation replaced with annual crops. No roots from natural vegetation to hold the soil in place. And then there was a severe drought. Winds blew soil as far east as New York City and DC, and then farmers went bankrupt. This was also during the time of the Great Depression, and we saw a huge migration of people from rural areas into urban areas because of the fact that farmers and their families could no longer farm, and they had to move to cities and acquire other jobs. Nutrient mineral depletion. Harvesting crops disrupts natural nutrient cycling, of course, because you remove the crop and then it takes some of the nutrients and minerals with it, right? Intense agriculture, exploitative agriculture that does not constantly replenish those minerals can really harm the soil health and even affect crop growth in the long run. Worldwide, more than 1 billion people depend on agricultural soils that are not productive enough to adequately support them. Unsound farming methods, extensive soil erosion, and desertification contribute to nutrient mineral depletion. So that is constantly happening. And here you can see how a crop plant, the minerals removed with the harvested material, then there's dead organic material. Minerals are added as organic or inorganic fertilizer, minerals in the soil, then the minerals are part of the soil. Sometimes there's mineral loss from leaching, what we really want is absorption of minerals by roots. But if it's too intensive, then this cycle becomes, this arrow here becomes more weighted and this arrow becomes less weighted, right? So this, there's more loss of minerals and crop health significantly declines. Soil salinization, we talked about saltwater intrusion in the last chapter. This can also happen with soil salinization. Gradual accumulation of salt in the soil, usually due to improper irrigation techniques. Here in the picture on the right, you can see a Colorado farm that has soil with white salt residues from improper irrigation. It often happens in arid or semi-arid areas that have high natural concentrations of inorganic compounds, such that are mineral salts. And because of this, the amount of water that drains into deeper soil is minimal because of the precipitation that falls quickly evaporates, leaving the salt behind. Basically, hot areas, evaporation happens quicker, the salt stays behind, keeps leaching into the soil, the salt concentrations can become high and toxic. Desertification. Asia and Africa have large land areas with extensive soil damage, and in both places, rapid population growth compounds this problem. So degradation of once fertile rangeland, tropical dry forest now becomes non-productive desert. And a lot of the causes, the same causes seem to be the problem: overgrazing, erosion, forest removal, and over cultivation. But what can we do to, stop or decrease soil degradation? Well, soil conservation practices promote sustainable soil use, and here are some of the best ones. Conservation tillage, which means working the land, include spring plowing, in which the soil is cut and turned into preparation for planting seeds, and harrowing, in which the plowed soil is leveled, seeds are covered, and weeds are removed. Conventional tillage removes all plant cover and greatly increases the likelihood of soil erosion. With conservation tillage, there is little disturbance to the soil. During planting, special machines cut a narrow furrow in the soil for seeds. Several types of conservation tillage fit different areas of the country and different crops. The most extreme of these, no tillage, does not involve any tilling of the soil, okay? So instead of just removing everything, they leave some of the decaying residues from the previous years to help remineralize, put nutrients into the soil. And what they found is that this type of tillage can reduce soil erosion by as much as 70%. So it's really impressive. I'm sure you've heard of crop rotations. This is something that has been stressed in school, but it's very simple. When the same crop is continuously grown, pests for that crop tend to accumulate to destructive levels, as well as the crop, if it does not have nitrogen-fixing bacteria, it can take all of the nitrogen that is found in the soil and basically deplete it of essential nutrients and minerals. So crop rotation would be planting a series of different crops in the same field over a period of years. So let's say you have 4 plots, right, in a square, right? So think of one big field and then you divide it into 4, right? You put a cross in the middle, and in the first top left one you put corn. In the top right one, you put soybeans. In the bottom right one, you put oats. And in the top and the bottom left one, you put alfalfa. Every year, you would move along kind of in a rotation. So in that way, the same crop is not planted in the same place. And it has proven to be very effective, and it's less damaging. So it's pretty good. Other types of conservation practices are more geological based and are contour plowing, strip cropping, and terracing. So plowing matching natural contour of land, strip cropping is alternating strips of different crops along natural contours, and terracing creating terraces on steep slopes to prevent erosion. In that way, the topography kind of basically stops the soil from being lost. Cover cropping. Crop planted primarily to protect soil from erosion after the harvest of one crop and before the next crop is planted. Otherwise, the soil lies barren and sensitive to erosion. So, after harvesting, sometimes you have to wait for the next season that you can plant in. Instead of just allowing the field to lay bare, people have put, a cover crop to protect the soil and make sure that it's not going to erode. The next one is types of fertilizers. So there are two main types, organic and commercial inorganic. Organic include natural materials like animal manure, crop residue, bone meal, and compost. They are chemically complex, slow acting, but longer lasting. The nutrients become available to the plants only as the material begins to decompose, which comes obviously from those microorganisms I mentioned earlier. Next, we have inorganic fertilizers that are manufactured from chemical compounds, and their exact compositions are not very known. They are soluble and they are immediately available to plants. However, what we have seen is that they're only available in the soil for a short period because they quickly leach away and may become oxidized in the air. In sustainable soil management, the use of these type of these fertilizers is avoided or limited. One, because of their high solubility, meaning that they can often be leached into groundwater or surface runoff, polluting the water. And second, because they do not improve they do not improve the water holding capacity of the soil as organic fertilizers. So it's basically teaching the land by providing just this readily accessible inorganic fertilizer. It's almost like teaching the land to not be able to support organic or like decomposition properly, right? So yes, inorganic fertilizers are not the best option. Soil reclamation. It involves two steps. It involves restabilizing the land to prevent further erosion and restoring the soil to its former fertility. Okay. And one of the best ways to do this is to plant shelter belts, which lessen the impact of winds. And it's a row of trees planted adjacent to a field of crops to reduce wind erosion, which you can see here. And to be quite honest, it's kind of visually appealing, so it's not too bad. Agroforestry. Organizations such as the International Center for Research in Agroforestry, established in Nairobi, Kenya, have developed techniques to lessen the environmental degradation of the Sahel in Northern Africa and other areas. One of their research aims is to use agroforestry, which is land use practices in which trees and crops are planted together to improve soil fertility in degraded soils. This is similar to crop rotation because obviously you plant a crop or a trees that can do nitrogen fixing alongside the traditional crops that you might need. So in Africa, they will plant nitrogen fixing acacia trees intermittently with the traditional crop of millet and sorghum. The trees, with their bigger roots, can hold soil in place as well as provide essential habitat for beneficial insects, as well as do nitrogen fixation, thereby improving soil fertility. And the crops obviously also provide food for people and for insects and nearby animals. So it's basically like an engineered ecosystem that's mutually beneficial to both humans and the environment. Soil conservation policies in the United States. Well, first we have the Soil Conservation Act of 1935, which, as I explained to you, was a consequence of the American Dust Bowl and brought about the Natural Resource Conservation Service, and they assess soil damage and develop policies to improve soil. In 1985, we got the Food Security Act that contained two main provisions for soil conservation: the Conservation Compliance Program and the Conservation Reserve Program. They both require farmers with highly erodible land to develop and adopt 5-year conservation plans for their farms that include erosion control measures. And if they don't comply, well, they lose federal agricultural subsidies such as price supports. And we also have the instituted and the Conservation Reserve Program, um, which pays farmers to stop producing crops on highly erodible land and then requires planting of native grasses or trees on such land, and then retiring it from further use for 10 to 15 years. So there are several things that the US government provides to farmers, particularly small scale farmers, to make sure that soil health, soil fertility is preserved. That's it for this chapter. Please let me know if you guys have any questions. Thank you.